Hello everyone. Last time we left off with a review of differentiation from Calculus 1, and now we start looking at our main goal for Exam 1, which is logarithmic and exponential functions. So this lecture probably will be in two parts, and we'll cover topics 1 through 3 on the homework, basically logarithmic functions and differentiation involving them. So a primary definition for a logarithm is a standard disclaimer: n greater than 0, b greater than 0, b is not equal to 1. We write log base b of n equals x, and that is referred to as our logarithmic form. And these double bidirectional arrows here mean if and only if, so you can go in both directions. We're going to change this to exponential form by taking the base of the logarithm b, raising it to the power x to get the number n, and that is our exponential form. So we have two logarithms that we most commonly encounter: log base 10 of n. Okay, I'm going to use a triple equality because you could read that as by definition or is always equal to. You'll never see the 10, it'll just be log of n. So it's understood, just like when you have a square root, that we don't write the 2 for the index, that when we have a logarithm and there's no base written, that it's 10. And then we have the natural log, which we're going to deal with most exclusively. And that's the logarithm with a base that's a number, represented by a letter. And that letter is the letter E. And log base E of n, you'll never see it written that way. It's going to be ln of n. And that's read as the natural log of n. Reason why the L comes before the N is in mathematics. A lot of the early math took place in Europe and a lot of French influence, and so log naturel, but we read it as the natural log of n. So this number E is very special. It's attributed to Leonhard Euler. And here's a definition for it. And it's approximately equal to 2.718281828 46, and then it goes on and on forever. It's an irrational number, transcendental, just like the number pi. Never repeats itself and never terminates. Now, just to get a sense of how this definition provides us with this number, let's create a quick table here. So I'm just going to choose values of x, and then look at the expression 1 plus 1 over x raised to the x power. If you start with 1, which is kind of silly because we've got to go to infinity, but if we plug in a 1, we get, I'll just do the side work here, 1 plus 1 over 1 raised to the first, and that would be 1 plus 1, which is 2 to the first, or just simply 2. Alright, let's jump up to 10, so that would be 1 plus 1 over 10 raised to the 10th, so that's 1 and 1/10, or 1.1 raised to the 10th. Alright, I'll go to a calculator, and 1.1 raised to the 10th is 2.5937, and it goes on and on. Let's just jump right away to 1,000. You can see how it's getting close to this, what we're claiming is the number E. Okay, if we go to 1,000, we get 1 plus 1 over 1,000 raised to the 1,000th. So that'd be 1.10 100,000th raised to the 1,000th. So that is 1.001 raised to the 1000 power. And that gives us 2.71692, and then a bunch of digits after that. So you can see right away, even at just 1,000, we're becoming pretty close to this number E. And the higher you go, the more accurate you're going to get. It's kind of interesting how the base, as the base of this expression converges to the number 1, and the power of the expression increases without bound, this expression provides us with this very special number. So another definition is for the natural logarithm that you probably haven't seen before. In terms of calculus, it's the definite integral from 1 to x of 1 over t with respect to t. And I guess I should have stated here that this is where x must be greater than 0. And graphically, what this means is that you have a vertical axis and a horizontal axis, and the horizontal axis is actually the t-axis. You can label the vertical as y. If we graph 1 over t, you can pick points if you want, like if you pick 1 over 1 is 1, pick 2, 1 over 2 is 1/2, pick 1/2, 1 over 1/2 is 2. But you should know the basic graph of 1 over t. It's what we call the equilateral hyperbola. It's in the first and the third quadrants, so that's what it looks like. So here's the graph of, let's say, let me call it f of t, is 1 over t. And it's really in the third quadrant as well, but as we've defined, x must be greater than 0, so we're not concerned about that. So what the natural log of x is actually the area, because we know that the definite integral gives us the area, under the graph of the curve 1 over t, from the vertical line x equals, that's right here, to whatever value of x you choose. And so that area in there is actually our definition for the natural log of x. Again, the integral from 1 to x of 1 over t with respect to t. Now, you're going to have to memorize this definition at one point when we get to a proof, but I'll make you well aware of that. Some observations that we can make are that if x is greater than 1, then the natural log of x is positive. It's greater than 0 because we get a positive area. If x is between 0 and 1, that would mean we're in this area, somewhere in here. We'd actually have to switch the limits of integration because we would have that this is the integral, let's say, I'll say it's 1/2 to 1 of 1 over t with respect to t. But it's a property from Calculus 1 that you might remember. You could switch the limits of integration, but it would be the opposite. So the integral from 1 to 1/2 of 1 over t with respect to t. So this ends up being negative. And then if x is equal to 1, well, you don't have any area at all, so the natural log of 1 is 0. So that's some things, some formal theory that, although you might not be tested on it literally, it's certainly something you want to know about. And then we get to the algebraic log properties. And the algebraic log properties are stated, I'm going to state them with respect to the natural log, because that's what we're going to be dealing with exclusively. We have the standard disclaimers, m is greater than 0, n is greater than 0, and p is an element of the reals. And so, natural log of a product, m times n, is the sum of the logs. Natural log of m plus the natural log of n. Now, these are proofs that you should have seen back in like an algebra and trigonometry class or maybe a pre-calculus class. They're very easy to prove. You just basically start in the logarithmic world, change over to the exponential world, perform some operations in the exponential world, and then change back. And so just remember the log of a product is the sum of the logs. And you could probably gather that if the product is a sum, quotient is the difference. The natural log of m divided by n is the natural log of m minus the natural log of n. And then we have the log of a power rule, natural log of m raised to the p power. Make sure you realize these are algebraic properties, nothing to do with calculus. Turns out you could swing the exponent p out in front of the natural log of m. But again, I know it almost feels like a calculus move because you're moving the exponent out in front, but you don't decrease the exponent by 1 or anything. It's just an algebraic log property. Now I'd like to state a general property. Let's assume that uppercase A, B, C, and D are some functions, and if we have the natural log of, let's say, AB over CD, to expand it in one step, what we could do is the following. If a factor is in the numerator, when broken down, the coefficient of the log will be positive, and if a factor is in the denominator, when we break it down, the coefficient of the log will be negative. So in one step with that general concept, we'll have the natural log of A plus the natural log of B, because A and B are both in the numerator, but then because C and D are in the denominator, minus the natural log of C minus the natural log of D. And just to show you the reason why this is true, because some of you might be thinking, well, C and D are being multiplied. You just said multiplication is addition, but here there's both negative. Here's the reason why. If you start with natural log of AB over CD and show these properties literally, we would first have to perform the quotient property. So natural log of AB minus natural log of CD. And then on each of those, the product. So the natural log of A plus the natural log of B, but then minus. But if I'm about to break this down into two terms, I need parentheses. And the natural log of C plus the natural log of D. And then that negative gets distributed. So we'll recopy natural log of A plus the natural log of B. Distributing the negative, we get minus natural log of C minus the natural log of D. So there's the general property shown. It's kind of helpful, as we'll see in our examples, when we either expand or contract. So here's some examples on the next page. So we're asked to expand, or in other words, write as the logs of the simplest things possible. Primarily in this example, the primary rule is the quotient rule. So natural log of x to the fifth minus natural log of y to the fourth. But then we can go further and exercise the power property for logs and swing those exponents out in front. So 5 natural log x minus 4 natural log y. And now we have these in terms of the logarithms of the simplest things possible. Now here's an example where that general rule is helpful, because we could just expand in one step. Again, if a factor is in the numerator, coefficient of log is positive. If a factor is in the denominator, coefficient of log is negative. So here we have natural log of x squared plus the natural log of y to the fourth, but then minus natural log of z cubed and minus natural log of t to the fifth. Oh, that's the way I make my z's. I make my 2's like this and my z's with it. Looks like a 2 with a little line through it, so just get used to that. Okay, but just as in the last example, we can simplify further by using the power property. So 2 natural log x plus 4 natural log y minus 3 natural log z and minus 5 natural log of t. Okay, so you'll see that this will become helpful in the differentiation process. We may have a need to condense, basically reverse the process, and if you look at these examples that we just accomplished, we're just going backwards. Last thing we did in the expansion was to bring down the coefficients, so that's the first thing we should do in the contraction or condensing. So we'd have the natural log of x to the 4th plus the natural log of y to the 7th, and then we recognize that this is the sum of 2 logs, which must have come from a product, so the natural log of x to the 4th, y to the 7th. This example will show how the general property is helpful. First step, once again, bring the coefficients up to be the powers on the arguments of the logarithms. So we have the natural log of x to the 9th. Leave the sign though, just bring up the magnitude of the number. So minus natural log of y to the 8th plus, bring up the 7, natural log of z to the 7th. Leave the minus, bring up the 6th, natural log of t to the 6th. And now in one step, with that general property, you can condense this. And again, if the coefficient of the log is positive, the argument is in the numerator, and if the coefficient of the log is negative, the argument is in the denominator. So x to the 9th is in the numerator, y to the 8th in the denominator, z to the 7th in the numerator, and t to the 6th in the denominator. So we're going to be using the algebraic log properties, as you'll see. And here's our theorem, which involves the derivatives of the natural logs. Now I'm going to use the shorthand notation. We'll say the derivative with respect to x of the natural log of x. Okay, you just have to memorize this formula. Again, it's common knowledge, so you do need to memorize it. And turns out, and we're going to prove it momentarily, comes actually from the definition, or it's a consequence of the definition of the natural log as the definite integral that we saw a little bit ago, that it turns out to be 1 over x. And this is provided that x is greater than 0. Now, I gave the disclaimer in the theorem, let u be a differentiable function of x. That's just a standard one. And so when we differentiate the natural log of u with respect to x, okay, there's a variety of ways that you can think of this, but here's primarily the way that I'm going to suggest. When we differentiate the log of a quantity, we get a fraction, and the logarithm goes away. And we put the quantity, in this case u, in the denominator, and its derivative goes in the numerator. And I'll denote that by du dx. Another way to think of it, so that's the way I'm going to be saying it, you could think of it as 1 over u times du dx. Or if you don't like the du dx notation, but just remember that's just differential notation to indicate the derivative of u with respect to x. But if you don't like that, you could say u in the denominator, u prime in the numerator, or equivalently 1 over u times u prime. So it's your choice, but I'm going to stick with this first version. And now we're going to prove it. So first off, let's repeat the definition for the natural log of x in terms of the definite integral. Okay, and this is what you're going to have to memorize. But before you get tested on this, we'll have a little quiz with a couple proofs in the very near future. And before we get tested on this, I will summarize this during our formal lectures, which are going to be Zoom sessions, as you know. And we have the natural log of x is the integral from 1 to x of 1 over t with respect to t. And you do have to include this in your definition, that x is greater than 0. So that's going to be worth like 2 points, just to be able to state that definition. Okay, and then we have the second fundamental theorem of calculus that you should have seen in Calculus 1. And it's the derivative with respect to x of the integral from a to x of f of t with respect to t. So it's kind of a special theorem. Very cumbersome to prove this theorem. It's about a page long in the textbook, which becomes 2 pages if you try to prove it. If anybody wants to see the proof, I'd be more than happy to discuss it with you, but I'm going to omit the proof from the lecture. Turns out that this becomes the integrand f of t, but evaluated at x. And this is provided that x is an element of the reals. I'm sorry, a is an element of the reals. So you have to state that as well. Okay, just an example so you see how this works. It might seem obscure, but as an example, if you had the derivative with respect to x of the integral from 1 to x of, let's say, e to the t squared with respect to t. See, the idea is that the function f of t is this e to the t squared, and everything else matches. You've got the derivative with respect to x out in front. A is your lower limit of integration, which is a real number. It's 1. It could have been 2, 3, some other number. But the x has to be the upper limit of integration. Then here's our function of t, the differential dt. Everything matches. The result is f of x. If f of t is e to the t squared, we're just replacing the t by x. So that becomes e to the x squared. Okay, so therefore our theorem is this. That the derivative with respect to x of the natural log of x is 1 over x, and formally provided that x is greater than 0. Oh, and I guess way back up here when I stated it with respect to u, I should have said u is greater than 0, just to be formally correct. Okay, so then the proof. The proof is just a matter of combining the definition with the fundamental theorem of calculus. I'm going to start with the given, that the derivative with respect to x of the natural log of x. Okay, but that's going to be equal to the derivative with respect to x. Now I'm just going to substitute the definition of the natural log of x into this notation. And here it is, up here, it's the integral from 1 to x of 1 over t with respect to t. You may think this is almost mathematical because we're pretty much done, but now we use the fundamental theorem of calculus and we realize that everything matches, just like in this last example. That is, the d dx is out in front. We have an integral. A is 1, upper limit x. Our function f of t is 1 over t. We've got the differential dt. And if the result of f of x and f of t is 1 over t, the result is 1 over x. Just replace the t by x. And that ends the proof. Okay, so that's my little signature box to indicate the end of a proof. Alright, so I'll remind you of when you're going to need to prove that, and we'll move on to some examples of finding derivatives. Actually, I think this is a good time to stop, and then we'll look at some examples of finding derivatives in the next part.